I'm going to talk about demystifying pageload performance with WProf. This is a collaborative work with Aruna, Arvind, and David from the University of Washington. So nowadays, web is everywhere. It is the critical part of the internet. Unsurprisingly, page load is critical. Studies suggest that Amazon can increase 1% revenue by decreasing page load time by 100 milliseconds. And unfortunately, page load is slow. Our own measurement study of the 200 websites, each with 5 rounds, suggests that the median page load time is 3 seconds. And a few web pages take more than 10 seconds to load. And if you are familiar with browsers, the page load time here means how long the spinner takes. Because page load is slow, there are many techniques that aim to optimize page load time. The optimization techniques include using CDNs, more page speed, SPDY, so on and so forth. So our own experience, as well as studies from others, suggest that while these techniques can help some pages, they may have no effect on some other pages, and in fact, they may even hurt performance. So the reason is that the page load process is poorly understood. So our goal here is to understand page load process. It is difficult to understand page load. The main reason is that there are many factors that affect page load. This includes page structure, the interdependencies between network and computation. So we know that network and computation activities inside browsers are intertwined. This also includes browser implementations. Different browsers may have a different set of policies. So next, we will give an example of how page structure affects page load. And it's easy to construct examples for the others. Here, we have 2 web pages. The first web page embeds a JavaScript and an image. The second page embeds this image and then the JavaScript. So these 2 pages look exactly the same inside the browsers. But we find that the first page takes longer to be loaded than the second one. So why? Now we look at the timings of loading the objects on the pages. So for the first page, we can see that loading this CSS waits until the JavaScript is loaded. The reason is that loading JavaScript blocks HTML parsing. And for the second page, we can see that loading this JavaScript does not need to wait until the image is loaded. So this is the reason that why the first page takes longer to be loaded than the second one. So if we look at the 2 pages, for the first page, all 3 objects here are the bottlenecks. But for the second page, only 2 objects here are the bottleneck. This means that dependency is important, and that understanding dependency is the key to understand page load. Here is an overview of our talk. First of all, we model the page load process, at the core of which is a set of dependencies that inherent in the web page. To implement the set of dependencies inside browsers to study on real pages, we built a tool which we call WProf. WProf automatically extracts dependencies. And to identify the bottlenecks of page load, we apply critical path analysis on top of the dependency graph we generated. And at last, we will review some experiment results that we load real pages using WProf. Now let's take a look at how we model the page load process. We basically try to answer 2 questions: how a page is loaded and how to infer dependencies. Now let me give you some background of how a page is loaded. Here, it is an architecture of browser. So there are basically 4 components here, which includes an object loader, an HTML parser, an evaluator, and a renderer. So there are 2 takeaways from this architecture. The first takeaway is concurrencies. These 4 components here can happen in parallel. The second takeaway is dependencies. one component can block others. So our work is to figure out when concurrency or dependency can happen. Now let's look at a workflow of how a page is loaded. A page load starts with a user initial request. And the object loader downloads the corresponding web page. Upon receiving the first chunk of the root HTML page, the HTML parser starts to parse the page and adds to the DOM. When it gets to the script tag, the HTML parser requests the embedded JavaScript. And the object loader requests the JavaScript and sends it for evaluation. Because both HTML parsing and JavaScript evaluation can modify the DOM, they cannot happen in parallel. So what actually happens is that the JavaScript evaluation stops HTML parsing. And after it is finished, it resumes HTML parsing. So now HTML continues being parsed and adds to the DOM. And at last, the rendering engine progressively renders the page, which includes both layout and painting. Now let's look at how we infer the dependencies. Our goal is to extract as many dependencies as possible across browsers. So our methodology includes 3 elements. First of all, we design test pages to systematically uncover dependencies across browsers. We also examine documents as well as inspect browser code when open source is available. Note that no single source here can provide a comprehensive view of dependencies, but rather they complement each other. Now let's take a deeper look at how we design test pages. We design test pages to systematically uncover dependencies across browsers. So we start by thinking about how the web pages are organized, how the web objects are organized within web pages. So for any given web page, an object can either embed another or can follow another. So here's an example of a web page. On this web page, it embeds a JavaScript, an image, and a CSS. The JavaScript can recursively embeds an image and an HTML. So this represents the relationship of one object follows another. And this represents one object embeds another. So any given web page can be assembled using these 2 elements. So for our test pages, we look at all pairwise objects, all pairwise objects of different kinds that represent the 2 relationships. So the kinds of objects can be HTML, CSS, JavaScript, so on and so forth. Now, we load the test pages from different browsers. We observe the timings from developer tools, which are available from all major browsers. Now we look at the 2 pages that we previously reviewed. The first page has a JavaScript and an image, and the second page has an image followed by a JavaScript. So for the first page, we can see that the image, loading this image waits until the JavaScript is loaded. But for the second page, loading this JavaScript does not need to wait until the image is loaded. And if we delay loading the JavaScript on the first page, the image is delayed as well. But on the second page, if we delay loading this image, the JavaScript is not delayed. So this means that on the first page, the image, loading this image depends on loading this JavaScript. But on the second page, loading this image does not depend on the loading this JavaScript does not depend on loading this image. Now let's look at the dependency policies that we found. We basically found 4 categories of dependency policies. The first category is flow dependency, which is the natural order that activities occur. An example is that we need to download an object before evaluating it. The second category is output dependency. It ensures the correctness of execution when multiple processes access to the same resource. An example is HTML parsing and JavaScript evaluation cannot happen at the same time because both can modify the DOM. The third category is lazy and eager binding, which trades off between data downloads and page load latencies. An example here is preloading. Preloading is an eager binding where browsers can preemptively load web objects which are embedded later on the page. The last category is resource constraint. It is a result of limited computing power or network resources. An example is that a lot of browsers allow 6 TCP connections to a single server. So if we want to load 7 web objects to a single server, the last one needs to wait until a previous one is completed. Now let's take a deeper look at an example of output dependency. This web page embeds a CSS and a JavaScript. So first of all, the HTML gets parsed. Until it gets to the CSS tag, it loads this CSS and evaluates it. So at the same time, when the CSS is being loaded, the HTML continues to be parsed. And until it gets to the script tag, it loads this script. And then the script is evaluated. So note that the script is not evaluated immediately after it is loaded, but rather it is evaluated after the CSS is evaluated. So the reason is that both CSS evaluation and JavaScript evaluation can modify the styles of the DOM, so they cannot happen at the same time. And after the JavaScript is evaluated, HTML parsing is resumed. So similarly here, JavaScript evaluation and HTML parsing cannot happen at the same time because they both can modify the DOM. And the order here is important. So we can see the red arrows here represent output dependencies, which ensure the correctness of execution when multiple processes access to the same resource. Here we look at a list of dependency policies that we found. We found 6 flow dependencies, 3 output dependencies, 3 lazy and eager binding, and 2 resource constraints. We also find that there are differences across browsers. So one notable example is that there is only one dependency that happens to IE, which is that CSS download and evaluation can also block HTML parsing, which suggests some inefficiencies here. So with a set of dependency policies, we need to implement them inside the browsers to study what the dependency is like on real web pages. So to this end, we build the WProf tool. So there are three elements inside the tool, including a profiling in browsers, generating dependency graphs, and analyzing critical paths. So here is an architecture of WProf. So this is a browser stack. The web page instances run on top of the browser extension or plugin level, which then run on top of the native browser. We choose to work inside the native browser, which means that we trade off the compatibility for more information that we can get from the native browser. The reason is that the browser extension or plugin level does not provide us with enough information. Our profiler is just a shim layer inside the native browser, and it does not require any changes to the functionality of object loader, HTML parser, CSS, and JavaScript engine. So we implement the dependencies inside the profiler, and then the profiler can output 2 kinds of information, which includes activity timing and dependencies. We track the dependencies by using HTML tags under parsing when an activity occurs. And our in-browser profiler is lightweight. Our evaluation suggests that it only has negligible performance overhead. We built our in-browser profiler on WebKit and extended in both Chrome and Safari. And it is written in C++. So with these 2 kinds of information, we do analysis offline to, first of all, to generate the dependency graphs, and then to identify the bottlenecks, we apply critical path analysis on top of the dependency graphs. Now let's take a deeper look at dependency graphs and critical path analysis. Here is an example of the dependency graph of the page on the left. The boxes here represent activities, which include loading an object, parsing an HTML, or evaluating a JavaScript or CSS. The arrows here represent dependencies. we can see that for a simple page like this, it results in a complex dependency graph. Then, let's look at how we do critical path analysis. We define critical path as the longest bottleneck path. So first of all, we look at the last activity. And then we recursively look forward to all the activities that the current activity depends on, and that happens last, which is this path. So a takeaway from the critical path is that for an activity that is not on the critical path, improving it does not help the page load time. An example here is loading this JavaScript. But however, if we increase the time to load this JavaScript, the critical path can be changed. So the critical path is really persistent per page load, but the dependency graph is persistent per web page. Now let's look at our experiments with real pages using WProf. Here is the experiment setup. We run our experiments at UW Seattle campus network using WProf instrumented Chrome. We look at 150 pages out of the top 200 Alexa pages. We repeat our experiments for 5 times and look at the minimum. The first question we try to answer is, how does computation contribute to page load time? So we've seen arguments, as we've seen that a lot of the optimization techniques are about to improve the network. So we are curious, are we solving the right problem? So here is the result of the critical path. The x-axis is either network or computation as a fraction of the page load time. So we can see that for the median case, the computation is 35% of the page load time on the critical path. So this means that both computation and network are significant. The second question we try to answer is, how much does caching help page load performance? As expectedly, caching can help a lot. So our results suggest that caching eliminates 80% of the web objects, but it doesn't reduce page load time as much. So why? By looking at the critical path using our WProf tool, we find that caching only eliminates 40% of the web objects on the critical path. This explains why caching does not help as much as we expected. We also have some other results and many more from our paper. For example, most object downloads are not critical, and JavaScript blocks parsing on 60% of the top web pages, while expectedly, synchronous JavaScript should be eliminated. There is some related work in this space. Our work is inspired by both academic and industry work. One industry work is the developer tools. It captures the timings of object loads, but however, it's unable to figure out which objects are on the critical path using developer tools. In academia, WebProf pioneered the research to understand page load time. It treats the browser as a black box, and it extracts dependencies between network loads. So it only considers network by ignoring computation. Our work is different in that we consider what actually happened inside the browser, which includes both network and computation, and we find that computation is actually significant. And we can easily run experiments with our tool at scale. So in conclusion, first of all, we model the page load processes and by extracting a set of dependencies inside browsers. To implement the dependencies inside browsers, we build a tool which we call WProf that automatically extracts dependencies and analyze critical paths. WProf can be used to, first of all, understanding performance of any web page load, to explain behaviors of current optimizations, and it can also be used to perform what-if analysis, which we have more results on. And thank you. I can take any questions.
Hello, this is great work, thanks. I'm curious as to whether the models you construct out of WProf will be able to sort of predict what the benefits from parallelization, like on multiple cores, will be. If you parallelize the web page load, how much will that help? Can your model predict such a thing?
So like on these slides, we show that we can do some what-if analysis. So we can definitely do that. So, but for the computational part, it includes like HTML parsing, CSS evaluation, and JavaScript evaluation. So I think the first two kinds, which are HTML parsing and CSS evaluation, they can be parallelized, but in the parallelized like architecture. But for JavaScript evaluation, it's hard to parallelize.
Right.
Yeah.
Thanks.
A very interesting paper.
Thank you.
But I think the most important insight I can get from your talk is that you push the JavaScript evaluation to the back, then download the object first, and everything will be fine. But however, there are many websites because they try to prevent callers to download the object and dynamically generate a URL inside the JavaScript. So you have to render the JavaScript and to get the Ajax and to download the objects. So if you push the JavaScript version to the back, and the user will have a very bad experience because they can download the object very, very late and render the page very badly. So how can you prevent that?
So we actually consider the case that you said. We actually load the real web pages, so also consider.
But have you also tried to render the JavaScript to see whether they have dynamically generated URI?
Yes. So we consider the dependencies that are generated by the JavaScripts as well.
Okay. Second question is that in your example, you are using, say, slide 5.
So yeah, I think we can discuss offline.
Okay.
There are other questions. Thank you.
Hi, Funu USSD. Right now, your tool outputs the critical path when the page is entirely loaded. I'm just curious, would your tool also give fine-grained measurement in terms of like, I might be only interested in certain objects in a page, like say a particular HTML frame, but not the entire page. So in that case, would your tool also output the critical path for the frame that I would be interested in? So
can you repeat your question?
Yeah, sure. So your tool output the critical path with respect to the page, the entire web page is downloaded. I'm curious, would your tool also be able to output the critical path that a certain component I might be interested in, but not the entire page?
Yes, I think it can do that.
Does it add additional overhead?
So you mean my tool?
Yeah,
so
right.
we said that we evaluated that, and the performance overhead is very negligible in terms of the page load time. But there is some like more CPU and memory usage at the maximum case. But for the average case, the performance overhead is negligible. So we can really do this in real time.
Okay, thanks.
Right, and God for UIUC. So great stuff. I think you said that you are basing the results on the minimum over 5 trials for each page. So do your conclusions change when you look at the median or even the outliers?
So because there is a large variation during page load, so we only look at the minimum. We don't look at the median case because that can be abnormal or something, and we don't look at the abnormal case. We just look at the normal cases.
Okay, thanks.
Thank you.